Hello, today we're going to cover the topic of Cauchy-Euler equations. And this name, Cauchy-Euler, gets mispronounced quite often. I've heard so many different ways to say it incorrectly, so I have this little way to remember how to say it. It's like Cauchy and Euler. Um, I like to say people's names correctly, so I just wanted to make a point of that for a moment. So in the previous sections, we've been working with higher order differential equations that had constant coefficients. The homogeneous term was sometimes, or sorry, the non-homogeneous term was sometimes nice, sometimes not. But now we're going to work with a special type of equation where we're going to see, whoops, I meant to have the highlighter. We're going to see x to the power to some power in each of the coefficients of y prime, y double prime, y triple prime, and so on and so forth. Okay, so Cauchy-Euler equations are the ones that have powers of x with the orders of the derivatives of y. The a sub n through a naught, those are just going to be numbers, some constants. Typically, we'll see that the power of x matches the order of the derivative. And although it's nice, like that's a cool pattern and all, it's not absolutely necessary in order to solve these differential equations. Okay. Now, because that that leading coefficient of the highest order derivative right here is equal to 0 when x is equal to 0, that's going to make us focus on an interval of definition. So we'll either have an interval of definition for positive values or for negative values, but never including 0. For the sake of discussion, we're going to focus on the second order case to develop the process. It can be extended to higher order cases. But to develop the process, we only need to focus on second order because we'll see what the pattern is that emerges, okay? We are only considering the case where g of x is equal to 0. If g of x was not 0, then we would have to use variation of parameters to solve for the particular solution, okay? And the book does have some problems that force you to do that, but that's not my focus for this section. My focus is more just the introduction to Cauchy-Euler equations and how to handle things when we're not dealing with constant coefficients. Instead, we're dealing with power function coefficients. So here's our process. In looking at this differential equation, the standard form that's up here, seeing that there are x's to powers next to each of the y's and y prime and y double prime and so on and so forth, that kind of leads me to believe that maybe y is not e to the mx, right? Because if y was equal to e to the mx and we had decreasing powers of x in each of the terms, there's no way things would add up to 0. So it makes more sense that our solution must be of the form that it's a power function. Y is equal to x to the m. And if that's true, then that means y prime would be m x to the m minus 1, just taking a derivative. And y double prime would be m times m minus 1 times x to the m minus 2. If we substitute this into the second order differential equation with the case where g of x is equal to 0, then what we get is this ax squared, that was already there, but then there's the m minus 1, x to the m minus 2, plus the bx, which was already there, but then the y prime part gets replaced with m, x to the m minus 1, and then this plus c was already there, and y becomes x to the m. And that's all supposed to add up to 0. Now, when we use the rules of exponents and we combine the x squared and the x to the m minus 2, you add exponents. So we have 2 plus m minus 2, which just adds up to m. Similarly, When in the second term, when we combine the x's there, we have x to the 1, x to the m minus 1. When those combine, we get 1 plus m minus 1, and that lands with an x to the m. And so when everything's simplified, we have an x to the m in common for all the terms in the differential equation. So we should factor it out and see what's left behind. At that point, once we factor out x to the m, what we're going to be left with here is just a quadratic equation. And we can expand it by distributing the m to the m minus 1 and combine any like terms and then use a quadratic formula to solve or factor to solve. Now, your book does make a point of simplifying this as much as possible and getting it into this particular form where your quadratic will be am squared plus b minus a times m plus c equals 0. I don't really think there's any need for you to memorize a particular form. We have a quadratic equation. The rules of algebra are ours to use, so we may as well just go ahead and combine all the like terms and factor as we know how to, and if it's not factorable, use a quadratic formula, okay? But this is the auxiliary equation for a Cauchy-Euler equation. And again, do not memorize it, just do the math, okay? You'll notice when I work through the examples, I'm not going to go back to that. I'm just going to go ahead and do the math. Now, we will have 3 different cases to consider depending on the roots of this quadratic equation, because m could end up being real and unique. It could be real and repeated, or we could come up with complex solutions. So case 1, we have real and unique, distinct real roots. So this is the case where we get unique zeros of our quadratic, m1 and m2. Then the general solution of the differential equation would then be y equals c1 x to the m1 plus c2 x to the m2. Let's go ahead and see an example that would give us this form. We're supposed to solve the Cauchy-Euler equation, x squared y double prime plus 5xy prime plus 3y is equal to 0. So right away, since it's Cauchy-Euler, we're going to let y equal x to the m, y prime equal m x to the m minus 1, and y double prime equal m times m minus 1 x to the m minus 2, and sub into the differential equation. So when we do that, the first term, x squared y double prime, becomes x squared m times m minus 1 x to the m minus 2 plus 5x, and we replace y prime with m x to the m minus 1 plus 3, and the y gets replaced with x to the m, and that's all equal to 0. Now the x squared and the x to the m minus 2, that's just x to the m. And the x with the x to the m minus 1, that's just x to the m. And the third term has an x to the m. So I will go ahead and factor that out. Factor out the x to the m. It leaves behind m times m minus 1 plus 5m plus 3 is equal to 0. So what's inside here, the x to the m equals 0, this would just result in x equals 0, which is the trivial solution. We're not going to consider that. That's not one that we're interested in. We're interested in non-trivial solutions. So here's our auxiliary equation. If I distribute and combine like terms, it is m squared minus m plus 5m is plus 4m plus 3. That's equal to 0. Well, this factors easily without me having to memorize what that form one was up above. It's just m plus 3 times m plus 1. So then m is equal to minus 3, and m is equal to minus 1. This means our general solution y is c1 x to the first m, so it's x to the minus 3, plus c2 x to the second m, which is minus 1. And that's it. That's all we got to do for that problem. So it's our general solution, and we're done. All right. The second case is where when we solve our auxiliary equation, we end up with repeated roots. Now, when we got repeated roots before, when we were dealing with the constant coefficients, that was when we would put a multiplier of x in order to make it so that we had linear independence. And the result would have come out if we used the method of reduction of order. That would have shown us that the x multiplier is the perfect fix. That's just what happens in the math. If we were to use reduction of order again on the repeated roots case, where the first solution is y equals x to the m, the method of reduction of order would tell us that the second one is y equals x to the m times ln of x. That would just come out. And so we'll go ahead and not do the reduction of order and just accept that the solution, when we have repeated roots, the second time the solution appears, we're going to put in an ln of x to fix things, okay? And that process is repeated no matter how high up we get. So if we had like 3 repetitions of m, then the first one would be c1 x to the m sub 1, and then we'd have c2 x to the m1 times ln of x, and then we'd have c3 x to the m1, and then another ln of x gets multiplied, and it'd be ln of x all squared. Okay, so a higher number of repeated roots just means higher powers of the natural log. That's it. So let's do an example that uses this. We're supposed to find the solutions for x cubed y triple prime plus xy prime minus y equals 0. So this one is higher order. We only use the quadratic to get the process started, but we can still work with higher order differential equations. So this one will be just a little bit more to deal with. Wait, you know what? Oh, sorry. This one will be a little bit more to deal with because it is a higher order. And so we have another derivative to get in here. So we're going to start off with let y equal x to the m. Y prime is m x to the m minus 1. Y double prime is m times m minus 1 to the x minus 2. And y triple prime is m times m minus 1 times n minus 2 x to the m minus 3. And sub into the differential equation. So when we do that, y triple prime, we're going to have x cubed, and the y triple prime is m times m minus 1 times m minus 2 x to the m minus 3, plus x times y prime, which is just m times x to the m minus 1, minus y, which is x to the m, and this is equal to 0. Okay, the x cubed with the x to the m minus 3, that's just an x to the m. The x with the x to the m minus 1, that's just x to the m. So I have x to the m in common for all 3. I will factor it out. That leaves behind an m times m minus 1 times m minus 2 plus m minus 1. And that's all equal to 0. So this is going to give us a third degree polynomial. And before I start multiplying everything out and making this kind of hard for me to factor, I want to make note that I have, if I am creative in how I look at this, I have an m minus 1 common in 2 terms. And so I should be able to factor that out. And that will help me a whole lot, because then when I multiply everything out that's left behind, it's just going to be a quadratic. So let's do that. We have x to the m times the x minus 1. After I factor out the m minus 1, I leave behind an m times an m minus 2 plus 1. And that's all equal to 0. Now, the m is going to distribute to the m minus 2, and what I finally have is x to the m m minus 1 times m squared minus 2m plus 1. That's all equal to 0. And the m squared minus 2m plus 1, that's a perfect square trinomial. It factors to be m minus 1, m minus 1. So altogether we have x to the m minus 1, m minus 1, m minus 1 equals 0. And so m is equal to 1 3 times. And so that means when we form the general solution, we're going to see that same thing showing up 3 times. We have y is equal to c1 x to the 1, which I'll just write as x, plus c2 x to the 1. But since that's a repeat, we're going to write times ln of x, and then plus c3 x to the 1. But now it's a second repeat, so we're going to multiply by ln of x all squared. And that is the general solution for that one. Let's see one more that uses, or where we see the repeated solutions and also throw in some initial conditions, okay? So with this one, we have x squared y double prime minus 3xy prime plus 4y equals 0. And the initial conditions are about y of 1 is 5 and y prime of 1 is 3. So again, we let y equal x to the m. Y prime is m x to the m minus 1. And y double prime is m times m minus 1 x to the m minus 2. And sub into the differential equation. When we do that, the first term becomes x squared. Y double prime is m times m minus 1 x to the m minus 2 minus 3x y prime is m x to the m minus 1 plus 4y, the y is x to the m, that's all equal to 0. Factor out the x to the m, it leaves behind m times m minus 1 minus 3m plus 4. Our auxiliary equation is m squared minus m minus 3m, that's a minus 4m plus 4, and that's 0. And this factors to be m minus 2 times m minus 2 is 0. So we get m is 2 twice. And that means our general solution, y, is equal to c1 x squared plus c2 x squared, but that repeat means we need to put in an ln of x multiplier. Okay, now we need to apply the initial conditions. We have what y is, we need y prime. Y prime would be 2c1x plus 2c2x ln of x plus c2 x squared times 1 over x. Okay, and I'm not going to bother to simplify that because I'm just going to plug in 1 from my initial conditions that are up here. Okay, so apply initial conditions. Y of 1 is 5. That's going to give us 5 equals c1 plus c2 times 1 times ln of 1. But ln of 1 is 0. So this whole thing goes to 0. And this means c1 is 5. We now look at y prime of 1 being equal to 3. That means 3 is 2c1 plus 2c2 times 1 times ln of 1 plus c2, x squared over x is just x, and that's just times a 1. And so it looks like the middle term is going to 0. We know c1 is 5. So we're going to substitute that in, and we have 3 is equal to 2 times 5 plus c2. 2 times 5 is 10, so negative 7 is c2. And then finally, the general solution is going to be y equals c1, which is 5, x squared, plus C2, which is minus 7. So we'll do minus 7 x squared ln of x. Okay? All right, next is the third case. We have complex roots. They come as conjugate pairs always. And in this case, we would call them M1 and M2. M1 is alpha plus beta I. M2 is alpha minus beta I, just as they've been in the past. And then the general solution would look at first like this. Y would equal C1 x to the alpha plus beta I plus C2 x to the alpha minus beta I. I want to just play with this a moment so that you can see a little bit of where things are coming from when we get the real valued solution. So I can rewrite this as y equals c1 x to the alpha times x to the beta I, just using properties of exponents, plus c2 x to the alpha times x to the beta I. Then x to the alpha is common to both. So I could factor that out. I get x to the alpha times c1 x to the beta I plus c2 x to the, I forgot a minus sign, minus beta I. And then we would have to get a real valued solution. So we'd go back to, I'm trying to think of the name of the, of the theorem that we use in order to get this. It's Euler's formula. I was struggling because we're doing Cauchy-Euler equations, and I'm like, no, it's not Euler. I just have Euler on the brain, but it is Euler. It's Euler's formula that allows us to get x to the beta I and x to the minus beta I in terms of a real valued function. Okay, so when we present our solutions, we want them written this way. Y equals x to the alpha, which we see that up there, but then it's times c1 cosine of beta ln of x plus c2 sine of beta ln of x. So it's not just an x in there anymore, it's an ln of x. And that has to do with the fact that we're not dealing with e to the mx anymore, we're dealing with x to the m, okay? So let's solve this differential equation. We're given x cubed y triple prime minus 6y equals 0. Okay, so we're going to sub y equals x to the m and y triple prime, which is m times m minus 1 times m minus 2, x to the m minus 3 into the differential equation. After you've taken enough derivatives of x to the m, you know the pattern and you'll know what y triple prime looks like. But if you need to, show yourself y prime and y double prime. Substituting these in, we get x cubed, y triple prime is m times m minus 1 times m minus 2, x to the m minus 3, minus 6, x to the m is 0. The x cubed and the x to the m minus 3 is x to the m, so we'll factor that out because it's common to both terms. Inside we have m times m minus 1 times m minus 2 minus 6, and that's all equal to 0. Now, unfortunately, this is not going to factor as nice as the previous one did, so I need to FOIL things out and see what this looks like, okay? So my auxiliary equation, that's what I'll focus on. We have m minus 1, m minus 2 multiplied together gives me m squared minus 3m plus 2, and then a minus 6 equals 0. Distribute the m. We have m cubed minus 3m squared plus 2m minus 6 is 0. When I'm looking at factoring trinomials, not trinomials, third degree polynomials, if there are 4 terms, I look to see if the first 2 terms and the last 2 terms can factor and leave behind something common to each other. And it looks like that will work this time. So the first 2 terms have an m squared in common. And when I factor that out, it leaves behind an m minus 3. The last 2 terms have a 2 in common. And when I factor that out, I leave behind an m minus 3. and that's all equal to 0. Now the m minus 3's are common to both terms, so I factor it out. And that leaves behind m squared plus 2, and that's all equal to 0. So I have m minus 3 is 0, and I have m squared plus 2 is 0. The m minus 3 tells me m is 3. The m squared is equal to negative 2, so m is plus or minus I square roots of 2. So this means this is equal to a 0 plus or minus square root of 2i. So alpha equals 0 and beta equals the square root of 2. Okay, so then we can form our solution. We have one real root, and then we have our complex conjugate pairs here. All right, so the general solution, y, is equal to c1, x to the first root is 3, plus x raised to the alpha is x to the 0, times c1 cosine of beta, which is the square root of 2, times the natural log of x, plus c2 sine of square root of 2 for beta, times the natural log of x. X to the 0 is just 1, so I typically would not write this. So I'll just write y is equal to c1 x cubed plus, oh, hold on, those should be c2 and c3 inside since I already used c1. Good catch there. So I have c1 x cubed plus c2 cosine of the square root of 2 times ln of x plus c3 sine of the square root of 2 times ln of x. And that is the general solution for this particular problem. And that is the last example for this set of notes. If you have any questions about Cauchy-Euler equations, please feel free to reach out.